Hello, this is a short video on the topic of tension forces and ideal ropes. You'll find in physics classes you deal with tension a lot. And a little anecdote, and this is true, I went through my entire first year physics course without knowing that the word tension was a synonym for force. I just thought it was something else that popped into these problems, didn't know how to deal with it. So I always refer to it as a tension force or the force of tension. I do not like to use the abbreviation T. I always like my forces to start with F, and then I use a subscript to tell me which particular type of force it is. So I'm going to show you here what's kind of special about tension forces. There's just a couple of things, and some of them are, in my opinion, kind of obvious, but I see students mess this up a lot. So let's look at this example here. This is what we refer to as an Atwood machine setup. It's just a simple pulley. And it's got some type of rope or cable or string wrapped around it and a couple of masses on either end. This is actually a clever way of measuring the acceleration due to gravity if we let this system go and measure its acceleration. I'm not going to get into that now, but if we were just asked to draw the forces on this, what would we draw? Well, you see we have two different parts of the system, so I'm going to show you how we would draw the forces on each part, both M1 and M2. Let's just start with M1. And of course, we always start with gravity because when we're near the surface of the Earth, it's easy to calculate. So I'm going to call this FG1. And it's very important when you have multiple parts of your system. Everyone's going to have gravity on it. Make sure you use a subscript to denote which one is which. So anything else that's exerting a force is going to have to be from something touching or making contact. And the only thing making contact here is this rope. So the thing about ropes is, and this is true of all tension forces, ropes can only pull. They cannot push. So if it's attached to M1 at the top, it can only pull upwards. It's never going to push down. I have seen people show me forces from ropes that look like they're pushing. And I always make the joke that you can't push with a rope. So I'm going to call this FT. Now you might think, well, wait, shouldn't you call that FT1 to distinguish it from the other tension? And I'll show you why I'm not going to. But that's the only thing touching. So I'm going to move on to mass number 2 here. I'll draw its forces in green. And of course, I'm going to have to draw a gravity force here. And I'll call that FG2. Probably a little bigger, just looking at the size of the object, although it's hard to tell. And there's actually two things touching it. There's the rope here, as well as the floor that it's sitting on. So that's two different forces. So I'll draw the rope first. Now notice the rope is attached at the top, which means it must be pulling upwards. Now that's an FT, and here's probably the most important thing to know about tension as you get into these problems, and that is that as long as we have a nice, frictionless, and easy to move pulley, that the tension will be the same throughout the entire length of the rope. So we don't have a different amount on the left and the right. Doesn't matter what's attached to it, the tensions must be the same. Now in a future chapter we will get to some problems where we have a very massive pulley. It actually takes a little bit of effort just to move the pulley wheel. Then the tensions are not going to be the same. But in this case, all the strands of the rope exert the same amount of force. We'll call that just FT. Now what other force would we have here? Because we're sitting on the floor, we have a normal force that would be pushing up, and I'll call that F sub n. So there you see it. Two diagrams for the two parts of this system here. Now let's look at this one. This is actually very similar. This is also an Atwood's machine kind of turned on its side, and we actually have very similar forces here. So again on M1 we would have FG1, and we have the force of tension up. And if we assume this is a very light pulley, then we also have the same amount of tension. And again, it must be this way. Now, it doesn't matter whether somebody is pulling M2 to the left or whether maybe we're just letting the system move on its own and it's moving to the right. The tension will not change direction just because of the motion. It's still going to be rightward because ropes can't push. What other forces would we have? We'd probably have an FG2. We have a normal force, and we probably have some friction. if, let's just say the motion is this way, and it doesn't have to be that way, I'm just saying it is, then we could draw kinetic friction force, and that would be a pretty typical example. So there's a good examples of how tension forces come into some problems and how you want to watch out for both how you draw the directions as well as how you note the names of them, because you don't want to look like you have two tension forces, and then you're going to run into a math problem in that you can't solve for two unknowns if you only have one equation. No, in these problems like this, with a kind of a nice ideal pulley, nice ideal rope, the ideal rope means there is no mass to the rope, nothing so heavy that we need to worry about how we're going to move the rope. It's just sort of a vehicle connecting the different parts of our system, and we'll ignore any of the mass that it may have because it's probably pretty light compared to the masses of the other parts of the system. So that's what we refer to as an ideal rope. So that's probably going to do it for now. Hopefully this helps you get through a few of these problems. Good luck.